Hey everyone, and welcome back for another deep dive
Yeah,
into some fascinating physics.
absolutely.
Today we're going to be talking about something called the cosmic no-hair theorem,
Okay.
and we're going to be taking kind of a unique look at it through the lens of entropy.
Right. It's sort of a thermodynamic perspective
Yeah, exactly.
on this classic idea.
So to get started, can you just remind everybody what exactly is the cosmic no-hair theorem?
Yeah. So the cosmic no-hair theorem is this idea that if you have a universe with a positive cosmological constant,
Uh-huh.
then no matter what the initial conditions of that universe are,
Hmm.
it will eventually evolve to a de Sitter spacetime.
So it doesn't matter if
Yeah.
it's clumpy or smooth or
Doesn't matter.
whatever it's going
It's going to iron itself out
to end up as this
into de Sitter space.
kind of boring to sitter
Exactly.
space-time.
Yep.
So, now we've talked about this before, and there are proofs for this that use Einstein's equations, right?
All right, so there's a classic proof by Wald that uses Einstein's equations
Yeah.
and makes some assumptions about the matter content of the universe.
Okay.
But the paper we're looking at today is taking a totally different tack.
Okay.
So this paper is called Cosmic Equilibration, a holographic no-hair theorem from the generalized second law.
Okay.
And it's by Sean Carroll and Aidan Chatwin Davies.
Hmm.
And what they do in this paper is they try to prove the cosmic no-hair theorem. But instead of using Einstein's equations, they use entropy.
Entropy.
Yeah, thermodynamics.
So how do you even begin to apply entropy to the entire universe?
Right. So the idea is that entropy in a closed system always increases
Right.
until it reaches a maximum.
Yeah.
And so the question is that what's happening with the universe as it's expanding and the cosmological constant is becoming dominant.
Hmm.
Maybe that is like a system going to equilibrium.
Okay.
And in fact, de Sitter spacetime has some properties that look like an equilibrium state.
Like what?
Well, it has a constant temperature, for one, and the density matrix for de Sitter space is thermal.
Okay. So there are some hints.
There's some hints there
Yeah.
that it behaves thermodynamically like an equilibrium system.
Okay. But how do we go from this idea of entropy in general to, including the entropy of space-time? Because that always seemed kind of confusing to me.
Right, and that's where we have to bring in something called the generalized second law of thermodynamics.
Oh, right. Huh.
So the regular second law of thermodynamics says that the entropy in a closed system will always increase.
Hmm.
But Bekenstein came along and said, well, what about black holes?
Okay.
Black holes have entropy too.
All right.
And so he came up with this thing called the generalized second law,
Yeah.
which says that we need to include the entropy of black holes when we talk about the total entropy of a system.
Okay, so the black holes themselves contribute to the entropy.
Yeah, and in particular, their entropy is proportional to their surface area.
Hmm.
That's a weird thing, right?
Yeah, it's not like what we think of with entropy of like a gas or something.
Exactly.
Right.
But it's this deep connection between gravity and thermodynamics that we don't fully understand yet.
So, okay, we have this generalized second law that includes black holes. But how do we go from that to talking about the entire universe, which might not be full of black holes?
Right, so that's where Raphael Bousso and Meta Engelhardt come in.
Okay.
They developed something called the cosmological generalized second law,
Okay.
which is sort of an adaptation of Bekenstein's generalized second law to cosmology.
Mm.
And in order to do this, they use something called Q-screens.
Q screens.
Yeah, what are those? So Q-screens are basically these giant imaginary screens that are foliated by what are called quantum marginal surfaces.
Quantum marginal surfaces.
Yeah, so a marginal surface.
Ah,
If you just have a regular marginal surface,
Yeah.
like in classical general relativity,
Yeah.
that's a surface that extremizes the area.
Okay.
So think about like a soap bubble.
Right.
It's going to try to minimize its area.
Yeah.
And so a marginal surface is something that extremizes the area, either maximizes or minimizes it. But a quantum marginal surface is something that extremizes not just the area, but the area plus the matter entropy outside that surface.
Okay.
And that whole quantity is called a generalized entropy.
Okay, so generalized entropy is like a combination of the area
Huh.
and the matter entropy.
Yes. And it's measured in Planck units so that you can actually add the two together.
Okay.
So a quantum marginal surface is a surface that extremizes that generalized entropy.
Hmm.
And a Q-screen is made up of a bunch of these quantum marginal surfaces
Okay.
that kind of slice through space-time.
So the quantum part of that is what's throwing me off a little bit.
Right, so it's not really full-blown quantum mechanics. It's
Mhm.
more like a semi-classical thing where you're taking into account the entropy of the matter
Okay.
along with the area.
So like a quantum correction.
Yeah, you could think of it that way.
Okay.
So the cosmological generalized second law says that the generalized entropy along a Q screen will always increase.
Okay.
And that's what Carroll and Chatwin-Davies used to prove the cosmic no-hair theorem.
So they're not using the traditional Einstein equations approach. They're
Right.
just using this generalized entropy
Exactly.
and Q screens.
Yep. They show that if a universe has a Q screen where entropy increases to a finite maximum,
Okay.
then that universe has to be asymptotically de Sitter.
So essentially, if the entropy is going to max out,
Right.
then it forces the space-time
Yeah.
into this
It has to be de Sitter.
de Sitter form.
Yeah.
That's really cool.
That's pretty cool.
So how exactly, I mean, it's amazing that they can do that, but how do they actually mathematically do that? How do they go from entropy to saying that it must be de Sitter space-time?
Right. So the proof has kind of two steps to it.
Okay.
The first step is they show that as a universe approaches maximum entropy, that puts constraints on the structure of a Q screen.
Oh.
So you can't just have any old Q screen if you want the entropy to be maximized.
Okay.
It has to have a certain structure to it.
Mhm.
And then the second part of the proof is they show that in order for a space-time to have a Q screen with that particular structure, it has to be asymptotically de Sitter.
Oh.
So it's like they box it in.
Yeah.
They say if the entropy is maximized, it has to have this kind of Q screen.
Mm.
And if it has that kind of Q screen, then it has to be de Sitter.
Okay, so it's like a two-step process to kind of force it
Yeah.
into that
Exactly.
shape.
Yeah.
So do they give any concrete examples of how this works?
Yeah, so they start with a really simple example,
Okay.
which is a homogeneous and isotropic universe.
Okay.
So this is like the most boring universe you can imagine.
Well, it's basic.
It's the same everywhere.
Yeah.
It looks the same in every direction.
Yeah.
And in that case, they can construct a Q screen very explicitly
Okay.
using Robertson-Walker coordinates.
Okay.
And they look at how that Q screen evolves as the universe expands and the entropy increases.
Oh, okay.
And they show three things. First of all, they show that the Q screen has to extend infinitely far into the future.
Okay.
Second, they show that the radius of the leaves of the Q screen,
The leaves.
so like the slices of the Q screen at
Okay.
different times,
Yeah.
they show that the radius of those slices has to shrink in a certain way as time goes on.
Mm-hmm.
And then finally, they show that that shrinking behavior forces the scale factor of the universe to approach the de Sitter scale factor.
Okay, so even in this like most simple case,
Yeah.
they can show that the entropy basically forces it to evolve towards a de Sitter's
Absolutely, right.
future.
Yeah.
Okay, and then do they go on to look at more complicated cases as well?
Yeah, so they also look at what are called anisotropic universes.
Anisotropic meaning.
So anisotropic means that it's not the same in every direction.
Okay.
So the universe could be expanding faster in one direction than another.
Okay.
And these are more complicated to deal with mathematically,
Okay.
but they can still show that in those cases, the same basic principle holds. So what they show is that in an anisotropic universe, the Q screen kind of gets squeezed towards the origin of the coordinate system. And using that, they can show that the average scale factor, which describes the overall expansion of the universe,
Okay.
becomes de Sitter-like.
Okay.
But then they also have to show that the anisotropy itself decays away.
Oh.
So that you're left with a universe that is both expanding exponentially
Mhm.
and is also isotropic.
Okay, so even if you start with something wonky,
Yeah.
it's still gonna
Yeah, it irons itself out.
smooth itself out
To de Sitter.
to this de Sitter.
Yeah.
Okay, so one thing I'm noticing that they keep coming back to is this idea of entropy maximization.
Right.
And I know that they use that to kind of simplify the proof.
Yeah.
So they're assuming that the entropy is globally maximized on each light cone.
Right.
Can you just remind us what that means?
Yeah. So if you imagine a light cone emanating from a point, they're assuming that the slice of that light cone that they're using for their Q screen represents the absolute maximum entropy that you could get on that light cone. So it's not just like a local maximum.
Yeah.
It's the global maximum.
Oh, okay.
And they use that assumption to simplify the proof.
Okay. And that basically guarantees that each slice
Right,
is
yeah.
going to represent that
It's not
maximum.
maximum entropy.
Okay. And is there any reason to believe that that's actually true?
So it turns out that if something called the quantum focusing conjecture is true,
Okay.
then this global entropy maximization is guaranteed.
So the quantum focusing conjecture,
Your QFC.
QFC, what is that?
So the QFC is basically a statement about how a quantity called the quantum expansion changes along a null congruence.
Okay.
So it's kind of like a quantum version of classical focusing of light rays. but it includes entropy.
Okay, so if this conjecture is true, then we know that the entropy will be maximized on each
Right.
light cone.
It guarantees it.
Okay, that makes sense.
Yeah.
Wow, so we've covered a lot of ground here.
We have.
A lot of really complicated ideas.
Yeah, this is definitely one of the most conceptually challenging papers we've looked at.
Yeah, definitely.
But it's also, I think, really, really deep.
Yeah, very, very interesting.
And it's pointing towards some really fundamental connections between gravity thermodynamics and information theory.
Yeah.
And we'll explore that more in the next part of the deep dive.
Absolutely. Okay, I can't wait
All right.
to hear what's next.
Yeah.
So we'll see you then.
See you then.
Welcome back to the deep dive. Last time we were talking about using entropy to understand the cosmic no-hair theorem.
Right. Trying to understand why the universe seems to be heading towards this de Sitter state.
Yeah, exactly. This like really simple uniform state.
Yep. And we were looking at a paper that tried to prove that using not Einstein's equations, but the idea of entropy in these things called Q screens.
Yeah, those giant imaginary screens made up of those quantum marginal surfaces.
It's exactly those surfaces that are kind of like entropy detectives.
Right.
They're looking for the spots in spacetime where the combined entropy of the area and the matter outside is at its maximum.
Right. And one of the things that we talked about was that they made this assumption of global entropy maximization on each light cone to kind of simplify the proof.
Yeah, and I think it's worth digging into that a little bit more because it's a pretty strong assumption.
Yeah, it is. So what does it actually mean to assume global entropy maximization?
Well, imagine you're standing at a point in spacetime and you shine a flashlight in all directions.
Okay.
That light will form a cone as it travels outwards, right?
Our light cone.
Yeah, exactly. And that cone represents all the events that could have influenced that point in the past, or all the events that that point can influence in the future.
Okay.
Now, the authors are assuming that when they pick a slice of that light cone to build their Q screen,
Right.
that slice represents the absolute maximum entropy you could possibly get on that entire light cone.
So it's not just a local peak in entropy. It's like the highest peak on the entire mountain range.
Exactly. It's like saying that no matter where else you look on that light cone, you're not going to find a spot with higher entropy.
Okay, so why do they need to make that assumption?
Well, it makes the proof a lot simpler.
Okay.
If you know that you're always dealing with the absolute maximum entropy, then you can rule out a lot of possibilities, and you can kind of zero in on this de Sitter solution more easily.
So it's like a shortcut.
Kind of, yeah, but it does raise the question of whether that assumption is actually justified.
Right. I mean, how do we know that entropy is always going to be globally maximized on each light cone?
Well, that's where things get a little tricky.
Okay.
There's no guarantee that that's always going to be the case.
Mm-hmm.
But the authors do explore some ways to relax that assumption.
Oh, okay. So maybe there are other ways to get to the same conclusion, even without relying on that global maximization.
Exactly. And one of the ideas they propose is to shift our focus from entropy itself to the area of these special slices on the light cones.
Okay, so instead of looking for the highest peak in entropy, we're looking for the slices with the biggest area.
Right. And in certain scenarios like Robertson-Walker spacetime, which is homogeneous and isotropic.
Same. Everywhere looks the same in all directions.
Yep. In those cases, they found that if you have a continuous holographic screen built out of maximal area slices, one for each light cone, then that guarantees a finite, globally maximal area slice.
So in those cases, the slice with the biggest area also happens to be the slice with the maximum entropy.
Exactly. And what's really interesting is that they demonstrate this connection without needing to invoke the quantum focusing conjecture.
Which we talked about last time as being one way to guarantee that global entropy maximization.
Exactly. So it's like we found a different route to the same destination.
Okay, so even if we don't assume the quantum focusing conjecture, this link between area and entropy might still be enough to point us towards the cosmic no-hair theorem?
It might, and the authors even hint that there could be other ways to relate area and entropy in this cosmological context that we haven't even thought of yet.
That's pretty cool. It seems like we're just scratching the surface of this whole area and entropy thing.
I think so. There's a lot more to explore here.
So where do we go from here? What are some of the next steps in this research?
Well, one thing that the authors suggest is to look at different functional forms for the gravitational contribution to entropy.
Okay.
So remember how we said that generalized entropy is the sum of the area of a surface plus the entropy of matter outside that surface?
Yeah.
The area part is supposed to represent the entropy of the space-time itself.
Right.
But what if that's not the whole story? What if there are other ways to calculate the entropy of spacetime that we haven't considered yet?
So maybe the area is just a first-order approximation.
Yeah, exactly. And by exploring those other possibilities, we might gain new insights into the nature of gravity and how it relates to entropy.
Okay, so that's one avenue for future research.
Yeah. And another really interesting direction would be to see how these thermodynamic ideas play out in the context of quantum field theory in curved spacetime.
Right, because in the real universe, we don't just have empty space-time, we have all these quantum fields fluctuating around.
Exactly. And so the question is, how does the presence of those quantum fields affect this whole entropy maximization picture?
And do they evolve in a way that's consistent with the universe approaching a maximum entropy state?
Right. And could we even see new types of quantum correlations or entanglement emerging as the universe approaches equilibrium?
Whoa, that would be wild. Entanglement playing a role in the long-term fate of the universe.
It's a very speculative idea, but I think it's worth considering.
It definitely is. This whole deep dive has been incredible. It's amazing to see how these seemingly disparate ideas, from gravity to thermodynamics to quantum information theory, are all coming together to paint this new picture of the universe.
I agree. It's really exciting to be working in this field right now.
Absolutely. So what's next for us in our deep dive?
Well, in the final part, I think we should step back and consider the bigger picture.
Okay,
What are the implications of all this for our understanding of the universe as a whole?
I like it.
And what new questions does it raise about the future of complexity in a universe that seems to be heading towards maximum entropy?
I can't wait to dive into those questions with you, so we'll see everyone in part 3. Welcome back to the deep dive. So we've been talking about this really fascinating idea of using entropy to understand the cosmic no-hair theorem.
Yeah, it's kind of a mind-bending concept.
It is, but it's also really elegant.
Yeah, there's a simplicity to it that's really appealing.
And I think in this final part, I'd like to kind of step back and think about the bigger picture. What are the implications of all this?
Yeah,
What
absolutely.
does it really tell us about the universe?
Well, I think one of the most thought-provoking questions that this research raises is what it means for the future of complexity in the universe.
Okay, so if the universe is really heading towards this maximum entropy state where everything is smooth and uniform,
Right.
does that mean complexity is doomed?
It's a question that's been debated for a long time, and there's no easy answer.
Okay, so give me some hope here.
Well, I think one possibility is that even though the universe as a whole might be approaching a maximum entropy state, there could still be pockets of lower entropy where complexity can persist.
Hmm. So even though the universe is getting smoother overall, there could still be regions where things are clumped together, like stars and galaxies.
Exactly. And those regions could potentially support life or other forms of complexity for incredibly long timescales.
So it's not necessarily a bleak picture of everything just dissolving into this uniform soup?
No, not necessarily.
Hmm.
I think there's room for both.
That's a relief.
Yeah, it's a much more interesting universe that way.
It is, and it makes you wonder about, the resilience of life itself and its ability to find a way, even in the most unlikely of circumstances.
Absolutely. It's a reminder that we shouldn't underestimate the power of life to adapt and thrive.
So what other big questions does this research raise for you?
Well, I think it really challenges us to rethink our understanding of the relationship between gravity thermodynamics and information theory. For a long time, these fields were seen as separate and distinct, but now we're starting to see these deep connections emerge.
And it's all thanks to entropy.
In a way, yeah, entropy seems to be this unifying principle that ties everything together.
It's like the cosmic glue.
Maybe so.
Wow. So
Okay.
we've covered a lot of ground in this deep dive. We've gone from coffee cups to black holes, from imaginary screens to the fate of the universe.
Yeah, it's been quite a journey.
It really has. And I want to thank you so much for being our guide through this incredible landscape of ideas.
It's been my pleasure. These are the kinds of conversations that I live for.
And to all of our listeners out there, thank you for joining us on the deep dive. We hope you've enjoyed exploring these fascinating ideas with us. And as always, keep asking questions, keep wondering, keep exploring, and we'll see you next time.